But if you take a look at this figure, the top one shows a representation of some kind of signal, and notice that the signal is continuous over time. And so this is what we mean by the term analog. Usually what we do is we have some kind of device called a transducer. So in physics, they call it a transducer. In engineering, they probably call it a sensor. But what this device does is it takes, on this side, some kind of physical quantity. And on this side, it converts it to either a voltage or current. An example of this would be maybe a microphone. So I can have maybe I got a microphone. This could be my transducer. And over here, I get sound. And over here on the other side, on the output of this, I get a current. So this signal that I'm showing you in the picture, if I go back to figure 1, could represent any kind of analog signal. On the bottom, this is process of quantizing, or turning an analog signal into a digital signal, which I want to discuss in just a second. But let me go back to analog. Just as an example, I want you to think about how a temperature might vary over time. So maybe I have this this apparatus to measure temperature over time. Maybe my time is 24 hours. So maybe we start right here at 12 p.m. And this device, whatever it is, records the temperature over time. So maybe the temperature does something like this. It's low, and then it goes high, high. Maybe it does something like that. If you notice, I didn't lift my marker off the board when I made the graph. It's a continuous line. This is a representation of an analog quantity. But if I wanted to actually do something with this in terms of using it with a computer or some kind of digital device, there's no way for me to put the signal directly into a digital device. And let me back up and talk about one important thing. I'm going to use the term computer. And right now, most of you are probably looking at me on you're watching this on a laptop, or maybe you have your cell phone. I wanted to define what I mean by computer, because even though this class is about PLCs, really we're talking about computers. And for the purpose of this class, a computer is anything that contains a microprocessor. A computer is anything that contains a microprocessor. And so if you think about the microprocessor, is actually think of it as the brain that makes what you call a computer work. Well, there are many, many devices other than your laptop that contain a microprocessor. An example would be your cell phone. Your cell phone contains probably several microprocessors. Therefore, your cell phone is, even though you call it a cell phone, it's a computer. You might have a microwave. If you can program that microwave, if it's a newer microwave, chances are it has a microprocessor in it. Therefore, your microwave, even though you call it a microwave, is a computer. If you have an automobile, a late model automobile, it has several microprocessors in it. So when I use the term computer or digital device, I'm not just talking about a laptop or a PC. I'm talking about anything that contains a microprocessor. Now, a PLC, as I said before, is a computer on steroids. So even though we're kind of addressing specifically PLCs, what I'm talking about right now is going to be true for any digital device. So what you have to understand is most quantities that we want to measure, most quantities in nature is like this. They're analog. But when I want to do something with that quantity in terms of using it, say, for automation or any kind of computing purposes, there's no way for me to put an analog signal to a digital, to a computer. I was going to say a digital. So we have to do something with it. We have to basically digitize a signal. So the first thing I want to talk about is how would I digitize a signal, and what do I mean by digital? So digitizing a signal is more of a process over time, and I have some kind of machine constantly record the temperature from 12 a.m. to 12 p.m. Now you could do the same thing. You can make a graph like this, but there's no way for you to continuously get this data in a continuous fashion from 12 a.m. to 12 p.m. What you're likely to do, if I tell you that, hey, go out and make a graph of temperature over time, what you're likely to do is get up at regular time intervals and check a thermometer and write the temperature down. So maybe you come in here and you take a measurement at regular intervals. And so maybe you get up here, maybe at 1 a.m. you come here and you take a measurement. And then here, you take a measurement. And then here, you might get up at regular intervals and take measurements. And if I make a graph, and hopefully this shows in the camera, if I make a graph of what you made, then your graph is going to look like this. Instead of having this continuous analog graph that you would get from some kind of sensor or transducer, what you'd have are these data points. And so at this time right here, you have a data point, and then here you have a data point, and then you have these data points. It might look something like that. And so if I go back to my picture, and you zoom in on that, you can see that the top signal is a continuous signal, it's analog. But what I want to try to do is to turn this into a quantity, or process this into a quantity that I can use in the digital device. And so at the bottom, it's important to understand that this picture here is not a digital representation of the signal, but the digitizing actually happens over here. So let me explain what I'm saying. So if I want to digitize a signal, continuous signal, I want to basically take an analog signal and turn it into digital information. This is not what I mean by digital. I have here that digital is a process. What you actually have to do is you have to go in and what you do is you sample these points, which is what you did when you took temperatures at an interval. So you got these data points now here. Then what you would do is something we call quantizing. You quantize it, meaning that you will give each one of these points right here what we call a binary value. And so binary basically is a code based on zeros and ones. So binary. So right now, just think zeros and ones, and we'll dig into that here in a second. So basically what you would do is you say, all right, I'm going to represent this piece of information using this code that's made up of zeros and ones. I'm going to represent this information. And since this data point is different than that, they're going to be represented by different codes. So maybe that looks something like that. So each one of these data points basically is assigned a number, and that number is a series of zeros or ones. So again, let me go back to the picture, and you can kind of relate the two. Okay, so if you zoom in on this, as I said before, the top represents a continuous analog signal. But if you'll notice at the very bottom, like this point right here. Hold on a second, guys. My eraser. So this point right here is assigned the value of all ones, and then this point right here, each one of the points on the bottom figure, each one of those little data points is assigned a value of zeros or ones. Hold on a second. I lost my. Okay. I don't know what happened. My eraser stopped working. So, all right. Sorry about that. So the process of digitizing, as I said, you take an analog signal, you basically sample it at a certain time, and then that particular point you would assign a binary code. So this point right here basically is assigned this number, and this point or this number right here maybe assigned to that point. And then what you would do is you would actually store that information, and that's the process of digitizing. So this is kind of a complicated thing to do, but computers do it all the time. We want to take analog information and we want to digitize it so we can use it in a device like a PLC computer or a cell phone. Now, if you think about it, if I compare these red dots to the green, if you think about what happens like between like this point and this point, if I blow that up, I got this point on the left, I got this point on the right, and then between them, I have some analog information. Basically, when you digitize something, you throw this information in between the two data points away. And you might wonder if that's good or bad, and the answer to that question is it depends. It depends on what you're doing with the data and depends on a few other things. What you could do, though, if you wanted to, let's say you wanted to get a better representation, a better digital representation of this analog signal. What you could do, maybe before when you got these data points, maybe you sampled every hour. You could, if you wanted to, come in here and maybe sample every half hour. And you can see by doing that, you'd have more data points. And so you'd have more points in between these points. But what's the disadvantage to that? Well, the disadvantage to this is that every point, every data point that you take has to be related or corresponds to a code that has to be stored. So this is called the sampling rate of a signal. When you sample a signal, the more often you sample a signal to quantize it, that is to turn it into zeros and ones, the more zeros and ones you have to generate, the more you got to store. So what you get is kind of a trade-off. The more you sample, you get a better digital representation of an analog signal, but you got to do something with those zeros and ones. You got to do two things. Number one, when you quantize, that is when you take a point from an analog signal and you assign this binary code to it, you got to store it somewhere. So you got to have enough memory to store it. And then usually you don't want to just store digital information. You got to move it around in some kind of digital circuit or computer or phone or whatever. And then you got to take that code and you got to move it from one place to another. So the more you sample, the more zeros and ones you have to store. And the more you sample, the more information, the more zeros and ones you gotta move around. So there's kind of a trade-off. Does anybody know what a Polaroid is? A Polaroid picture. Anybody ever heard that term before?
an Instamatic camera?
What is it? Yeah, you've probably seen that where you take an Instamatic camera, you take a picture, and at least in the old days, you could do like this, and the picture would develop in front of your eyes. A Polaroid camera takes an analog picture, and if the best way to explain it is to think about the colors. Maybe colors, they kind of go, they don't go from one color to another. They kind of go through a gradient. And so it's an analog representation of whatever you're taking a picture of. Let's say I use a Polaroid camera and I take a picture of a person. So I take a picture of a person. Not this, excuse my artwork, but here's a picture of a person. But this is from a Polaroid camera, so this is analog. Now let's say I make a copy of this and I give it to the newspaper. Maybe they did something special. I don't know, maybe they won the lottery or something. So they're on the front page of a newspaper. So they take a Polaroid picture of them and they give this to the newspaper, and they're going to run this in the newspaper. And so in the newspaper, you'll see a picture of the person. But if there was a way to expand this picture, if you make this big enough, what you see is that in the picture in the newspaper, the one that was not taken with the Polaroid, or if you use a digital camera to take the same picture, if you make this big enough, what you will see is that each line that you think is the line is really a series of lines. And so this line right here that makes up the person's body is really a series of points, and each point is a pixel. And that pixel, what that is basically what we said before, is just a bunch of zeros and ones that represents a certain, in this case, color code, a certain color or value. Why would I want to have things represented in a digital way, a digital form? Well, it turns out, and I've already kind of answered that, we live in an analog world. Most of the quantities we as people, at least on the macro level, most of the quantities we deal with, like pressure, sound, those are continuous. But anytime you want to do something in a computer, again, a computer is anything that has a microprocessor in it, you got to go from analog to digital. And so when you make a phone call on your cell phone, you're speaking into the microphone, the sound that you're making, that's analog, but when it goes into the cell phone or when it goes into the computer, it's got to be changed to digital. So that turns out to be vitally important. Well, in a lot of ways, digital it has a lot of advantages over analog, but there's two I want to make sure that you're clear on, that we understand before we leave the lecture today. Since each one of these points right here basically is represented with zeros and ones, a binary code, that number that's stored can be repeated over and over and over again, and it doesn't degrade. Now let me see if I can give a better example of that. Now I don't know how old you guys are, and you grew up, you probably listen to music on your cell phone, but I'm old enough to know, I remember when records and cassette tapes. So when I was a kid, we want to buy some music, we go and we get a cassette tape, and basically, hopefully you know what a cassette tape is, a recording of music. Basically a cassette tape is just plastic with rust on it, and they use magnetism to store sound. Okay, but it's analog. So I could go to the record store or go to the store and buy a cassette tape of your favorite artist, whoever it may be. I don't know who you listen to, but let's say I'm listening to I don't know, Lil Wayne, whoever you listen to. So I go get this cassette tape and I'm listening to some music. Well, what you can do is you can actually dub it. You can record it. So maybe I'm listening to this cassette tape of Lil Wayne, and my buddy comes and say, "Hey Ron, let me borrow that cassette tape. I want to make a copy of it." Now remember, the information on the cassette tape is analog. So I said, "All right, I'm gonna loan you this tape. You go ahead and dub it. You make a copy of it, but make sure you give me my cassette tape back." So he goes and he makes a copy of it and hands me the original back. I have the original in my hand, and he's listening to the copy, but maybe he has a buddy that wants a copy. So he gives them the copy that he made. And long story short, if you keep making a copy of a copy of a copy of anything that's analog, over time it's going to degrade. Analog degrades over time. Whereas if I digitize it, if I instead of having it on a, maybe I record it on a tape, if I use a CD records zeros and ones. And so basically that number, since it's a code, that code can be repeated over and over and over again, and those zeros and ones stay zeros and ones. They never degrade. So one advantage digital has over analog is that I can make a copy of a copy of a copy, and it never degrades. So I want you to remember that, because I'm going to ask at some point about the digital advantage. What advantage? There's several, but there's two main advantages digital or digitizing has over analog. And one of those advantages is that I can make a copy of a copy of a copy. And in theory, I can make as many generations as I want away from the original, and that copy will be exactly like the master. So in theory, digital does not degrade. So if you're taking notes, write that down. The second advantage that digital has over analog is this. If you know what a cassette tape is, and I use that example, I'm old enough to remember those cassette tapes. You could buy them in 30-minute lengths, you could buy them in 60 minutes. You couldn't get much over a 90-minute tape, because as you get more tape, they made the tape thinner, and the thing had a thick size, so you can only get so much tape on the spool. Well, since you only had a 90-minute tape, you can only store so many songs. If you digitize it, then this is basically, since you're storing zeros and ones, you can actually use algorithms to do what we call compression. You can put more digital information in a much smaller space than you could analog. I mean, you can compress analog, but no way near with the amount that you can compress digital. So the second reason for digitizing information, part of the digital advantage, is that I can compress digital information. So the digital advantage number one, if I digitize or quantize analog quantities, I can make a copy of a copy of a copy, and it never degrades. And the second important thing, the second important point for the digital advantage, is that I can really compress digital information. I can compress it. And I have another example here, just to kind of drive this point home. A couple more examples. So here I kind of used the microphone already as an example, but here you have sound, which is a physical quantity that's analog in nature, is continuous. And so this microphone right here, that's the transducer. Think of a transducer as a device that it takes in energy in one form and puts it out in another form. So it's going to take in this sound, which is mechanical energy, and change it to an electrical signal, either current or voltage. But notice, if you look at the signal here, notice that that signal is continuous, and this linear amplifier, you know what an amplifier does. Basically, what you have over here is just a bigger version of what's over there. We say it's amplified, so when you listen to the sound coming out of the speaker, it's going to sound louder. But this signal on the left and this signal on the right, they're both analog signals. On the bottom is a digital example. Here I have a CD drive, an optical drive. And basically what's recorded are these zeros and ones. So you can see, I don't know if you can see that I wrote on it, but right there, there's a series of zeros or ones there. And that's what, when you record information in the digital format, that's what gets recorded are those zeros or ones. And you got to go through a process, but this is kind of hard to see. But this right here in that box is kind of grayed out. It says digital to analog converter. We'll talk about what that means. But basically what this device does is it takes these zeros and ones and changes it back into an analog signal, and then I can run that to my linear amplifier. So stuff like this is done all the time in systems, and we'll talk more about some more examples of this. So I don't feel like I did. Hopefully you guys can follow what I said. It's kind of hard for me to explain this without having you guys in front of me. So
Personally, it was pretty.
somebody summarize for me. If you had to explain to a kid the difference between analog and digital, how would you do it? Anybody?
Analog is a physical representation, like a mirror, and then digital takes that representation and changes it so it's simpler.
Okay. And it changes it by taking a sample of the analog signal and then assigning zeros and ones to it. Nicholas.
Hi, do you hear me?
Yeah, I can hear you, Nicholas.
All right. If I may give it a shot.
Go ahead.
So some of the earlier like analog computers were things that were created to physically represent whatever you were trying to measure. So like some of the earliest analog computers were calculating the movement of the sun. So they were analogous to the movement of the sun. The gears and stuff inside moved at the same rate of that thing. And then digital is literally just any computation involving digits. Is how I would explain it.
Beautiful. And what I like about that definition is you can really compare the two. If you can compute something or you can represent something using digits, then you can repeat those digits over and over and over again because that's what you're recording is the digit. So I feel okay about this. I didn't know how good of a job I did in explaining these. But in the time that we have left, let me get just into the digital part of this a little bit more. We'll come back to this. One thing I want you guys to remember is this, though. You're surrounded by computers. Don't just think of a computer as the thing that's in front of you. Computers are everywhere. If you have a garage door opener, it may have a computer. It probably has a computer or a microcontroller in it. So any information that goes inside that thing that we call digital has to be ones. That code. What is exactly a binary code? So you probably heard about machine language. They talk about machine language, and what you have, like when I showed the example of the quantizing process, you saw that each data point from the analog signal was represented by a binary code. I believe they use 8. I'm using 4 here just for an example. But each one of these numbers, we call this a bit. A bit. And a bit is just a binary digit. And what they did, they took the B from here and the I key from there, and they just made up this word called a bit. So just kind of in a nutshell, think of a bit as a 0 or 1. And most people say, well, this is what computers understand. Well, they really don't. All a computer, and again, a computer is anything that contains a microprocessor. The only thing a computer can understand is the absence or presence of a voltage. Microprocessors, computers understand the absence or the presence of a voltage. And so what we do is we use something called two-state electronics. Two-state electronics to represent these bits. And basically, we have a voltage level, and we have another voltage level. And we assign these two voltage levels either to be a 0 or 1. Now typically, and what we'll do in this class is we'll have a voltage level of 5 volts, or we'll have a voltage level of 0 volts. If my voltage level is 5 volts, we're going to call that a 1. If my voltage level is 0 volts, we're going to call that a 0. These are binary over here. And these are actually voltage levels over here on the left. And so when I had that code a second ago, I had a code, maybe it was a 1, 1, 0, 1. That could represent one of those points in the analog signal that we talked about. Either it could be it doesn't matter when you think about a digital device, let's say you take a picture with your digital camera, you take a picture, you make a movie, maybe you have a movie, you make a movie, or you speak into a microphone, or you use a Word document. When you press enter, it doesn't matter whether it's a movie, a video, a Word document. When it goes into the computer, it goes in like this. So if there was a way to look in, if you took your cell phone right now, you may have videos in your cell phone. I'm sure you got pictures in your cell phone. You got all kinds of information in your cell phone. If you can lift the hood of your cell phone and look into the microprocessor, into the memory, all you would see are zeros and ones. And you couldn't tell if you're looking at a picture, a sound, or a Word document because they all look the same. Anything that goes into that device is stored as a 0 or 1. But really, it's not zeros or ones. It's the presence or absence of a voltage. Now, we're going to use, for our two-state electronics, we're going to use for this class 5 volts represent a 1 and 0 volts represent a 0. So what you would have here inside the device, you have 5 volts. Then you have 5 volts again. And then here you would have 0 volts. And then you would have 5 volts. And you might say, well, what do you mean? Where's this located? Well, a long time ago, they used something called a capacitor. You may have heard of a capacitor. And they actually still use these to store values. A capacitor is a device that you can charge up, and it can hold a voltage for you over time. So maybe I have 4 capacitors. I got 4 capacitors like that, and to get this one right here, I charge that capacitor up to 5 volts. To get this one right here, I charge this capacitor up to 5 volts. This one I don't charge up at all, and this one I charge up to 5 volts. So physically in the machine, you have some way of storing voltage or not storing a voltage, and they actually still use capacitors to do this. If you ever buy a computer and they use the word dynamic, like dynamic memory, it's memory that has to be refreshed because they have these little microscopic capacitors to store the zeros or ones. But really, you're not storing a 0 or 1, you're storing a voltage or you're not storing a voltage. I don't want to get into the physics of this. There's a lot of ways to do it, but when they talk about machine language, the actual machine language is the presence or absence of a voltage. We just abstract from that as humans, as people, and we like to think of it as zeros or ones. Anybody have any question over that? So I think I got a couple more minutes. Let me make this graph for you because I want to show you one more thing and then we'll call it a day. You can, this is ideally, in a perfect world, if I have 5 volts and I have 0 volts, so if I have 5 volts, I'm going to call that a binary 1. 0 volts, I'll call it a binary 0. Now, this is ideal. Well, actually, that's not what happens. Let me go to this other picture. So actually what happens is, let's see if I can take a look at this. Now, if you zoom in on this, and don't worry about the TTL and all of that. I just want you to kind of focus on the picture. So it doesn't matter if we look, we can use the graph on the left or right, it doesn't matter. But there's actually, instead of having like exactly 5 volts, well, then we're going to call that a 1, or exactly 0 volts, we're going to call that a 0. In the real world, what you have are these ranges. And so they're showing the range over here. Like over here, the range from this whole range right here, from 2.7 up to 5. Anything in that gray zone right there, this particular device for this graph is going to interpret that as a 1. And down here, in this gray zone on the bottom, anything between 0 and 0.5, it says it's going to interpret that as a 0. And so in the real world, you have more of a situation like this in the actual device. Now, we're going to use the ideal graph I showed you on the board, but just, I just want to mention that we're using these figures down here, which are ideal. But in the real world, you have this range. Now you might wonder, okay, well, I get it. If something's down here, it's going to count as a 0. If something's anywhere between over here 2 and 5, it's going to count as a 1. What do you think is going to happen if I get something like right here in between? Let's say for this picture, if I get something between 0.8 and 2, how's the microprocessor going to interpret that? It's going to interpret it as a 0, or is it going to interpret it as a 1? And the answer to that question is, we don't know. We call that the forbidden zone. You're not allowed, however your device is set up, like over here, you're not allowed to operate in this zone. If you operate in that zone, then your results are going to be unpredictable. And so we have circuitry in most digital devices to make sure that doesn't happen. Make sure you're not in the forbidden zone. So again, we're going to use this ideal graph here. When we talk about zeros and ones, just think of this one, but I wanted to point out to you, but there's actually a range. Are we o'clock? What time?
It's 9:55. I think we have till 10.
Okay. Yeah. So let me go talk about one more thing, and then we'll call. I think I got a couple more minutes because we're going to lose Monday. We don't have class on Monday, so I'm going to get as much in as I can today. But let me pause for a second because I said a lot of stuff. And does anybody have any questions or comments on anything I've talked about so far? Anything that you want to say a different way, or anything that might not be clear? Anything I need to go back over? Okay, well, the main thing is that what we got to do to use a digital device, PLC computer, we got to be able to take, the machine has to be able to take a physical quantity, which most likely is going to be analog in nature. It's got to be able to turn it to zeros and ones, which is what the machine understands, even though we really understand that a 1 is the presence of a voltage and the 0 is the absence of a voltage. So we got to be able to store information, and we do that in the form of zeros and ones. The other thing we got to be able to do is once we get that information stored, if I have a digital device with zeros and ones in it that represents a picture or sound or Word document, it's useless if I can't move it around. So I got to be able to do two things. I got to be able to digitize it or quantize it, change it into a 0 and 1. And once I get it in the form of a digital or binary code, I got to be able to move it from one point to another, either in the same device or maybe over the internet, or I just got to be able to move those bits around. And so I won't be able to go into all of that today, but I want to show you the kind of the way to think about that is this, a digital pulse. So zoom in on this, and we got 2 pulses here. In figure 1-6, compare the pulse on the left and the pulse on the right. So notice the one on the left, it starts off low. Now, when they use the term low and high, if it's low, that means 0 volts, and our high here is going to be 5 volts. So when they use the term low and high, they mean 0 volts and 5 volts. So right here, we start off at 0 volts, and then we go up. Right here, we go up to 5 volts. We stay at 5 volts for a certain amount of time, and then we drop back off to 0 volts. We call that a positive going pulse. Whereas on the one on the left, we start off at 5 volts, and then we drop down to 0 volts, and we stay at 0 volts for a certain amount of time, and then we go back up to 5 volts. They call that a negative going pulse. Now, let me just show you in the real world, there's something wrong with this picture, and actually I can show you down here. In the real world, the pulse looks more like this. See in the picture that I'm showing you here, the one in figure A, in this picture, we go from 0 volts up to 5 volts instantaneously. And what they're trying to show you down here on the bottom is, actually what you have is it takes time to go from 0 to 5 volts. So it takes some time. So you got this little rise time over here, and it also takes time to go back to 0 volts. So you got this fall time down here. Now again, in this class, we're going to use these ideal pulses, but in the real world, I just want to point out, you don't really have a perfect, this is called a square wave. you don't have a perfect square wave. It looks more like what's on the bottom here, but we're going to use ideal values here. So we'll deal with perfect square waves. So this kind of sets me up to talk about, and I'll come back and I'll probably review this on Friday. This sets me up to talk about, we want to understand now, how do we, once we've quantized analog information, once we've taken the value, a piece of the analog value, and assigned zeros and ones to it, and stored those zeros and ones, how are we going to move it around either the microprocessor, or how are we going to move it from one device to another? So that's the question I'm trying to answer. And the first step to understanding that is understanding what a digital pulse is. So I'll review this again on Friday, and then we'll talk about how do I move these bits around from one place to another. So I think that's going to be it for today. Let me go back to the camera and see, does anybody have any questions or comments or just anything before we sign off?
I've got a question unrelated to the current topic, but more about the simulator program we're going to be using.
Okay, shoot. I'm ready.
I've noticed some people have had problems finding it through the IP that you posted, and separate to that, is there a reason we're using such an outdated version of the programming?
When you say outdated, what do you mean?
I mean, Logix 500 hasn't really been a mainstay or standard for, what, 10 or 15 years at least now?
You mean Logix Pro?
Well, the 500 version of it, right?
Yeah, I think the idea here, though, is just what we're going to use. It's not so much the technology or the software. Really what this class is about is just learning how to write, and it sounds like you know a little bit about the programming language, just how to use ladder logic. So really all we're going to use, we're just going to use a program to write ladder logic program. So that no matter which simulator you use or which PLC, it's pretty much the same. The language we're going to use is the same. So I don't think really that's going to be too much of an issue.
I was just more thinking about if people were to step into the field, the automation field, it's kind of a rougher transition moving from the older programming to the newer programming, especially if you're talking with the Rockwell's current studio or even stepping into Siemens, the Somatic or the TI7. It feels like a very drastic difference.
Yeah, and again, I'm just wanna. It sounds like you're talking about the actual. Are you talking about the PLC hardware? Because
I'm just talking about the actual programming aspect of the Logix 500 Pro.
Okay. All right. Maybe we can talk more about that. Because again, I think if and I don't know if I'm being clear or not, but if you just focus on the ladder logic, then I don't really think the family of PLCs or the brand, I don't really think that matters. This is more of a generic general class just to kind of give you an introduction to ladder logic. We're not gonna talk about specific technologies or specific PLCs. It'll just be a kind of a general overview of ladder logic, and you should be able to take what we talk about and just, I mean, the learning curve to go from one PLC to another, the instruction set's going to pretty much be the same. We're going to use really, really basic instructions. So it's not, and if I'm understanding you correctly, I don't think that has been an issue or is going to be an issue. Now, we're kind of stuck with it. And as I said before, I don't know if you were with me on the first day, but the class was set up a little bit different years ago. We actually had a physical PLC. I don't know what it was because I taught more of the theory, and Mark Fassler taught the actual, whatever the PLC he used and the logic he used. He taught that part of the class, but they've gotten away from that. So we're kind of stuck with the simulator that we have, and the only one I'm familiar with is the one that we've been using for a couple of years. Now, if you know another simulation software, I'll be interested in hearing about it. But the school's not going to get an actual PLC. I mean, we have it here where I am now, but I'm not at UC right now. So we're kind of stuck with what we got, and that's kind of a UC thing. It's not anything that I can do anything about. But maybe we can have a conversation. We can just you and I maybe, and you can tell me a little bit more of your concerns. I just think that this class is really general, and as you'll see when you get into the programming of it, the lateral logic that we're going to use can be used anywhere. I don't think that's going to be an issue. As far as where to the simulator, where to get it, there's a website called, you got to put the Learning Pit. So the Learning Pit, and if you go there, you'll see there's a link where you can go and actually download that software, and I think it's like, but what I would do if I were you, I would, before you get to, because some of the lab manuals will come with a CD that has a simulation software on it. So before you go here, since you got to get the lab manual, I probably would get the lab manual first to see if you get the one with the CD in it, you never have to do this. You don't have to pay the $45. I've seen students get a lab manual for $5 or $10, and it has a CD in it included, so you don't have to pay the $45 or $35 or whatever it is for the simulation software. So, but if you just want to see what it looks like or download a trial version of it, you can go here and look for the trial version of Logix Pro. It kind of mimics the Slick 500 PLC, and then you can download and kind of look at that and see what I mean. But we kind of just stuck with that simulator, and it's really the cheapest way to go, because the schools, they're not going to get the kind of technology you're talking about. There's no way. I mean, I would love it, but we're kind of stuck with what we're stuck with. Who am I talking to, by the way? Is it Mike?
Yeah, Mike. I apologize. I'm a senior automation engineer for eTechnologies Group.
Maybe you can teach the class.
I actually run our apprenticeship program at our company.
Maybe what we can do, we'll talk by phone or something, and maybe you can give me some ideas. I don't know, but we'll talk. We'll talk by, is it Mike Tomer?
Yeah, I can shoot you a call after this if that text number
works.
Yeah,
let's do that. Matter of fact, go ahead and text me right now, and I'm going to text you when I get off of this camera, I'll text you my office number. You can call me. So go ahead and shoot me a text, and then I'll send you back my office number. And does anybody else have a question or comment? Kyle, Nicholas, Christopher, Jacob still on there, and then I got some other people. Well, there's a lot of people still there. Anybody else before we sign off?
Do you usually post the videos for the quizzes like right after class?
No, I don't. That one, well, there won't be videos for the other quizzes. That was just something really meant to be to do two things. Number one, I don't know how good of a job I did in explaining relays. I want you to really I think he did a really good job in the video. And the second thing was to give you an easy A for the first video for the first quiz. So no, there's usually no videos posted. It was just for that particular one. And the quiz, to be honest, I was struggling with that. And, I do better face to face than I do kind of through this camera thing. And for the last 2 years, we've been doing this thing because of COVID. So I have everything set up through Canvas. Is kind of automated, the quizzes and all of that. But before I would just go pass out paper and we have quizzes on Friday. Well, that's not the world we have right now. So I'm not really sure, but with the numbers that we're having as far as the COVID numbers, I'm not even sure. I don't want to predict what the school's going to do, but I'll be surprised if we really get back together in another 2 weeks or whenever they tell us we should get back together. I'd be surprised if we do. So I guess the point I'm making is if I keep the class like it's been for the last 2 years, you'll just go on a certain day. I'll give you a day when we're going to have the quiz, and you'll go, and it'll be kind of automated where you go on. It'll be like multiple choice, or you'll go online, and so it won't be a video like it was for that first quiz.
Okay, that sounds good. So there's not one after like every lecture day?
No. The next one, that one I want. The only reason I made that due so close to when I assigned it is I wanted to make sure that today everybody understood what a relay is and how it works. So typically there'll be, I might even, last time I taught the course, I think I assigned the quizzes on the weekend or something like that. So you'll have time to do it. It's not going to be an issue at all.
Okay, that makes sense and sounds good. Thank you.
Were you able to do the first one? You didn't miss it, did you?
No, I was able to. There was another class that we have that has a quiz after every lecture, and I didn't know if this would be the
No, I'm
same.
not. No, oh, God, no, I don't. I got
Okay.
enough to do already.
That
You're
sounds
fine.
good. Thank you.
Okay, thank you. That's a good question. Anybody else? Okay, well, Chase, Nicholas, Mike, Christopher, everybody else, thanks for hanging in there. I will see you guys Friday, and then we don't have school Monday, so we'll see how this goes. You guys have a great rest of the day, and I'll see you on Friday.
Thank you. You as well.
Have a good day.
Thank you.